Hello, am I audible? So we started discussion on SVM, support vector machine, and in our last class we have discussed one example data set. Okay, the data set is given and how to solve uh, our SVM problem. So in this, in that example, we have discussed about this. That is, the at first we discussed about how to get those equations. Okay, specifically the optimization equations, and also uh, and we have used the Lagrangian optimizer to find out the different equations. Okay, different equations, and using those equations, if the data set is given, then at first we need to the select our support vectors. So these are the support vectors in this case. Uh, Positive, in positive side we have taken A and B, and in negative side, sorry, in negative side we have taken A and B, and positive side we have taken just C. Okay, considering that, we have that is solved the problem, the SVM maximization and minimization problem. Okay, I think you understand this, but we didn't complete this example because we have only determined the Lagrangian constant values. So these are the values we have determined. These are the values we have determined. And also the B is here, but I forget to mention about the W. That means how to compute the W. I think you also know that how to compute it, because we have the equations. Equations are there. Uh, so using those equations, we have to find out the W. Like here, from these equations, we can see that is in Lagrangian equation, when we take the partial derivative of Lagrangian equation with respect to W, we got this equation. Okay? We got this equation. So to compute the W here, this vector, we can use just this formula. So here is alpha I and yi. We know the alpha I, we know the yi, and we also know our xi. That is, this is our support vector. Okay? Support vector. So different support vectors for like support vector A, support vector B, and support vector C. So it means that from this equation, we can also derive the value of the W. So in that equation, it is mentioned that here the W alpha I and then yi and then the xi. We can say that this is xi is our kind of support vectors here. Support vectors. This is the vector given vectors I, and this is the summation. It is equal our W. So now if we put the values like here, I one time is A, another time is B, another time is C. So because we have three support vectors, the equation we can write this equation like alpha A and then y of A, and also the xi of A, we can write like xi of A. It is our xi, that is xa, support vector A, plus of alpha B, that is the next support vector. We have another support vector taken, that is the B, and y also B, and also we have x, that is B, plus of uh, another support vector we have considered. Another support vector is alpha C, yc, and xc equal our vector W. Okay, now we need to just put those values till students are joining. Okay, now we can see that alpha a equals 0. Okay, we got alpha a equals 0. So here is the 0 times, and y is what? Ya, this is the class level of our a. So class level of a, if we can see here, the class level in our data set. So class level of a and b is negative, and class level of c is positive. Okay, so a and b is negative. So in this case, we can see the negative means -1, -1, and then xa, our support vector a. So support vector a, in this case, we can see our support vector a is 0, 0, and b is 1, 1, and c is 2, 0. Okay, so support vector a is 0, 0. Now plus of alpha b. So alpha b, we got alpha b equal 1. So here is alpha b equal 1. Alpha b equal 1 times then yb is our, that is class level of b. So class level of b is also -1. So negative times times um, xb, that is the support vector b. So support vector b is 1, 1. Okay, support vector b, the vector is 1, 1, and plus of then alpha c is 1 times, that is class level of alpha c is 1, that is positive, and support vector is what? Support vector, it is c is 2, 0. Okay, c is 2, 0. This is actually our w. Okay, so now we can write from here, we can write 0 minus 1 here is 0, 0. It means we will get the 0 plus of, so then 1 minus 1, and here is a 1 and 1. So we will get like -1 and -1, this vector, plus of, there is 1, 1 and 0, 0. So that means we will get like 2 and 0. So here is the 0, 0. Now if we add these three vectors, there is a 0, -1 and 2. By adding these three vectors, we will get -1, here is a +2, that means 1 we will get, and 0, here is -1, here is 0, that means -1, 1 and -1. So this will be our w. Okay, this will be our w. W is 1 and -1. So if we got 1 and -1, then the next thing is 1 and -1. Okay, then the next thing is uh, how to find out the equation of our hyperplane. So hyperplane equation, we know that hyperplane equation is what? W transpose x plus b equals 0. Okay, b equals 0. So this was the equation of our hyperplane. We derived this equation. So now if we put the value of w, so we can see w transpose. So w is 1 and -1. So if we transpose it, then we will get 1 and -1, -1. And for x, you can see that this is two-dimensional data. So that means hyperplane equation, in this case, it will be a line. Okay, so we will have just x and y on that case. That is x and y. We say x and y to get the line equation. Plus of b. So b, we got the value of b here. B is -1. Okay, -1. So b is plus of -1 equal 0. So now we can see that from this we can find out the equation 1x, that means x minus 1y, so that is y minus y, and then here is the, for b it is plus minus, that is minus 1 equal 0. So it means that this is our hyperplane equation in that case, okay? X minus y and 1. So if we really plot our data and see our hyperplane, then we can see here. Um, so consider that this is our just, maybe you can say the plot. So here is at first the point A, B, and C. That is our support vectors. So if we consider our support vectors, here is A is 0, 0, B is 1, 1, and C is 2, 0. A and B negative, and rest C is positive. So if we plot those 3 points here, so A, that means 1 is A. So A will be here. It is 0, 0. The point is 0, 0. This is A. And we can consider this is 1 and here is 1. So that means B, maybe we will get B here, this location. This is our B. And B in this case 1, 1, 1, 1. How about the C? C is 2, 0. Okay, so 2, 0. Consider that maybe you can say 2 is at this position. 2 is at this position. So 2, 0 is this one. So this is our C. This is our C. And C is 2 and 0. C is 2, 0. So A, B, and C, we got this. Now we can see that where is the hyperplane? The hyperplane. So A and B, these two, A and B is negative. So this one is negative, and A is also negative. Okay, so A is also negative. This point is negative. This two is negative, and this is positive. Okay, C is positive. The point C is positive. So now hyperplane, it should be maybe placed at the middle of between these two. Okay. So now we can say hyperplane equation is this one. This one is our hyperplane equation. X minus y minus 1 equals 0. So then if we can draw our hyperplane, then how can we draw that? So consider that at first y equals 0. If y equals 0, y equals 0, then in this equation, if we put here 0, y equals 0, then we can see y equals 0, x minus 1 equals 0 on that case. That means x equal 1. On that case, x equal 1. Okay. Now consider that if that equation, if x equal 2, so put the value of x here, x equal 2. So x equal to here 2 minus y minus 1. In that case, we can see 2 minus y minus 1, that means 1 minus y. So it is y equal minus y equal minus 1, that is y equal 1. On that case, y equal 1. We will get y equal 1. So now, based on these 2 points, we can draw our hyperplane. So y equals 0, x equal 1. So x equal 1, where is x equal 1? This is our x equal 1 and y equal 0. So that means this is the point. One point we will get here. And another point is x equal 2. So x equal 2, that means x equal 2 is at this point. X equal to, on that case, x equal to y equal 1. So y equal 1 means here. the point will be at this position. So if we just connect these 2 points, okay. So this is the hyperplane, and we can see that this hyperplane actually separate positives from the negatives. Okay, this is how we have to draw the hyperplane equation also. Is it clear? Okay, now I think we need to continue our discussion. Uh, the next thing is actually we already discussed about this constant. This is called the SPM with hard constant. Okay? And following that, we have already solved the problem. Okay, SPM with hard constant. So SPM with hard constants. So this is the equation, and we solve this equation using optimization problem, and also solve our one of the examples for that. Now, why the hard constants is actually not desirable? Why hard constants is not desirable? So sometimes we can see that actually we can see that here if we consider that is the hard constants. On that case, so if this is the data set, so we can see that if we consider cross and also the circles, we want to separate cross and circles, then all the cross are maybe we can see in this side and circles are in this side, but only one cross is here and one circle is there. Then what we have to do, that means maybe we want to draw the that is the separable line, that is the hyperplane, but we can see that at this in this case there is no way to get that is linearly separable line for that. Okay, maybe we cannot draw just this line, so we can say this kind of line, this kind of hyperplane to separate positives from the negatives. So what we have to do on that case, we need to think about non-linearity. Okay, non-linear separable line. But SVM actually it has different approach to solve the non-linear problem. Not like this. That is, we can draw like maybe the polynomial line like this way. Okay, like this way. So this is not the approach of support vector machine. So it will select differently. Okay, so that means and in another case what we can do, we can allow few misclassification for the linear separation. For the linear separation we can allow misclassifications here. So that means if we allow one misclassification of cross symbol and one misclassification of our circle symbol, then it's easy. The solution is easy. Okay, we can just draw a linearly separable line. So this is one aspect of that is considering the soft constraints instead of hard constraints, because you can see if we apply hard constraint, then it is problematic to solve this kind of problem. And another approach is this, that is why another reason we have. So another reason here is this, that is consider that in our training data set, we have all these, that is, we can say the red circles. These are, that is, the people with no obesity, and these are the people with obesity. Uh, so that means these are the people with no obese, and these are the obese people. Now, if we consider that this is our data set, according to our hard constants, actually, if we want to place our threshold, then where we have to place? We have to place at this position. We have to place the threshold at this position. So this will be our threshold. Okay. That means this will be our splitter, or you can say this will be our support vector. Sorry, this will be our the hyperplane, like this way. Okay, if we place the hyperplane at this position, because of the hard constants, because of the hard constant, this will be our hyperplane equation, or you can say threshold. But now, in test case, if you can see that in test case, we got observation this is our observation, the black one. If we got this observation, then it will classify as no obese. Okay, no obese. So that means this one classify as no obese. No obese. Okay, so this will classify no obese. But we can see again that intuitively, that is actually most of the data points of this test case is closer to obese people. You can say most of the data points. Actually, the distance from this one to our uh, the obese people, we can say average distance, is minimum than the average distance of this point to our no obese people. No obese people. Actually, those are very far from this one, and only this one is very close. Sometimes maybe you can say this is outlier. It can be outlier. Okay, it can be outlier, and based on the outlier, we train our model, and also place the hyperplane at the middle. Okay, and that's why now it will consider as a no obese, but we cannot interpret this result. Why? Because we can see that uh, the distance from obese people to this point is actually closer. So intuitively, it should be obese instead of no obese. So that's the problem of hard constants. Okay. So if we apply, that is sub constants, if we apply the sub constants, then what will be the case? The sub constants in training time, actually it will allow this misclassification. It will allow this misclassification, and the threshold it will place at this position. The threshold will place at this position because it will allow this misclassification. This is misclassified in training time, but now in testing time we will get the better results. Okay, we will get the better result. That means uh, for the case of our this new data point, based on our actually sub constants, we will get the threshold at this point. So now we can see this is actually classified as the obese instead of no obese. So now we can explain this answer, because this is obese because most of the obese people's data are close to this data point. So that is valid, that is intuitive. Okay, that's why we need to convert our hard constants equation to a soft constants equation. That means we should allow few misclassifications here. So now the point is, okay, we will allow misclassification, but we should not allow many misclassifications. So that's why the equation will be in our previous case. This is the equation. This is the equation, and we have to actually minimize this based on this constant. But now here, this is the additional thing. That means we have to allow few we can see here the number of mistakes, but we should not allow many. Okay, that's why we have to add some penalty for each and every misclassification, so that it will not allow many misclassifications. Okay, that means for each and every misclassification there we must add some penalty. So this is C. This C is our penalty term. Okay, so the value of C, this is sometimes we call also regularization parameter, and we discussed about the regularization also in our there is the linear regression, and there is the uh, elastic net regression, phase regression on that time. Okay, so we know what's there. Uh, so we this is also called the regularization parameter, and we can find out the value of C using cross validation. So, but now what we have to see that there is that maybe we need to penalize our mistakes if it and our model will allow mistakes, but we need to penalize it, so that we should not consider many mistakes. And now we can see that here for the penalization and also the mistakes, we need to how many mistakes we need to consider that, and then we have to consider that there is all mistakes are not the same. Okay, all the mistakes are not the same, and that's why we have added here the xi of I. What is the xi? Is the distance from, we can say this is the garter. This is the garter, that is we can say the positive garter from our positive misclassified positive instances, and similarly negative garter to negative misclassified instances. So the distance, actually the distance. So we will because we can say this mistake and this mistake is not same. Okay, this mistake and this mistake is not same, because we can say if one mistake is very far, that will not be the same as the a mistake that is very close to a hyperplane. So now we can see that there is a summation of all this. That means all these the distances we can add, and then for each and every one we will add the penalty, that is the C. And here the C, how can we determine the C, or what value will be the C is appropriate? If we consider that, if we assign the C value, that is the very large number, that means very high penalty, a very high penalty. So if this one is very high penalty, then actually this model, it will not allow any misclassification again, because for a single penalty it will get the hues. Okay, that's why you can see here there is it will not get the we can say it will not allow any misclassification if we set the C value as the very high. But again, if we set the C value as very low value, very low value, very low value, then it will allow many misclassifications. So if it allows many misclassification, then that's also problematic. Okay, that's also problematic, and that's why we have to think the C values maybe it's kind of, that is the middle values within 0 to 1. Hello. Uh, am I audible now?
Yes, sir.
Okay. Okay. Thank you. So now we can see that there is the same constant, that the number of mistakes. This one, we can now represent that one using a loss function. Okay, the loss function. The loss function we can represent using this. This is called the hinge loss. So the C, this is our the weight of the penalty, that is usually we call it stabilization parameter, and this is our loss function. So this is called the hinge loss. It means that there is, if there is any penalty, then it will add this the penalty term, or we can say it will incur the penalty like this. Okay, this much penalty, and if it is not misclassified, then there will be no penalty for that. Okay, let's say in this case it is a max of maximum. Max is maximum, so here is the 0, and 1 minus of, this is yi, and then this is our w transpose x, that is the wxi plus of b. So plus of b. Okay, so if we consider that, there is um, this is the original y. Okay, original class level, that is yi, and this is our prediction. Okay, prediction of our support vector. Okay, prediction of our support vector machine, SVM prediction. Okay, and based on the hyperplane. Then if this one is positive and this one is also positive, like positive 1, and it will also just return this positive 1, positive value, any positive value it can return. So like maybe the positive 2 or something. So it means this is positive, originally it is positive, and also our model will mention that that is positive. Okay, so in this case we can see from if we multiply these two, then we will get the 2, and here is 1 minus of 2. So the 1, this is 1 minus of 2. So we will get what? We will get the negative result. We will get the negative result. So that means any negative value, like here is a negative 1 and here is 0. Which one is maximum? 0 is maximum on that case. Okay, so 0 is maximum. Then this part, it will return 0. It will return 0, and 0 times c, that is our 0. It means that actually it is correctly classified, because original class level is positive and our model is also mentioned that it is positive. So that means this is correct classification. For the correct classification, it will not add any penalty. And for incorrect classification, let's say uh, our actual model is negative. So that means the actual answer is negative 1, but our model returned that positive value, like positive 2. On that case, if we multiply these two, then we will get, that is uh, negative 1 plus of positive 2, that is the negative 1. Sorry, that is the positive 1. And here is 1 minus of, no, this is multiplication. Okay, minus 1 times plus 2. That means if we multiply these two, then we will get the minus 2. So here is the minus 2. Okay, we will get the minus 2. So then 1 minus of minus 2, it is what? Minus minus plus. That means we will get the positive 3. Positive 3. So 0, and here's the positive 3. Which one is maximum? Positive 3 is maximum. Okay, positive 3 is maximum. Then 3 times c, that will be the penalty. Okay, 3c, that is 3c. The penalty will be 3 times c, that is 3c. Okay, 3c will be the penalty. And in this case, we can say 3c will be a penalty because original class level is negative and our prediction is positive. So that's why the model is penalized. Okay, model is penalized. So this is how the Hind's laws, actually Hind's laws uh, will guide the SVM, the support vector machine classifier, for correctly selecting the W and D. Okay, W and D. So that means now this is our actually the equation, or we can say objective function to solve our problem. Okay, so we have already discussed about how to solve the SVM problem, and using the method we have discussed, that is the Lagrangian method. Okay, Lagrangian method. Okay, we can apply again the Lagrangian method to solve that problem also. There is an actually easiest way to find the solution also, solution um, of our that is linear problem. Even non-linear problem we can also solve that in different way. So consider that a data set is given. The data set is given. So data set, this is our data set. If we plot, then this will be our data set. We can see that actual data set will be. So we have two features in this case also, like x1, x1, and x2, and also the class levels are given. The class levels are given. So for the first point, if we consider that this is our first point, okay, this is our first point. It is 1 and 1, so 1 and 1, and class level is what? We can consider that these are the negative class. Okay, these are the negative. In our data set, it will be given the negatives, and then we can say maybe this one. This one is what? X1 is 1 and x2 is negative 1. So 1, negative 1, and it is also negative. Maybe we can consider this one. So this one is our, it is x equal 2 and y equal 1, and also it is negative 2. And then another one, this one, this is x1 equal 2 and y1 equal negative 1, negative 1. And for that case, it is also negative plus, negative plus. Okay. Now we can say that this is our another data. So here is the 4 and 0. This is positive class, so positive 1. And then this one we can say this is our 5 and 1. So 5 and 1, also positive. And this is our 5 and negative 1, positive 1. And then 6 and 0. So here it is 6 and 0. It is 6 and 0. So 6 and 0 is also positive 1. Okay. So that means if any data set is given like this, this is a data set is given. So what we have to do at first, for solving this one, at first maybe you need to plot this one to for manual solution. You need to place this like this way, and then we need to find out the support vectors. Okay, the support vectors. To find out the support vectors, what we have to do to find out the support vectors? Maybe we can say we can consider maybe like this way, that way. Okay, different lines. Okay, different lines we can consider. But for finding out the support vectors, at first, maybe you can say you can consider any of those. In this case, you can see this can be considered as the support vector. We can consider this one as the support vector 1. We can consider this one as the support vector 2. So this is a support vector 2. And then uh, we can consider this one as the support vector 3, support vector 3. And we know that that is the support vectors usually we have to find out, that is considering our hyperplane, the closest distance data points, usually we have to consider the support vectors from both of the sides. Okay, so here is the S1, S2 and S3. And the convention is, if we have two-dimensional data, then it's better or at least D support vectors. Okay, so here is, we can consider D plus 1 support vectors. Okay, so now so if we consider our support vectors like here, this one S1, S2 and S3, our support vector, then the S1 is what? S1 is our 2, 1, and S2 is 2 minus 1, and S3 is 4 minus 0. Okay, 4 minus 0. Okay, 4 minus 0. So these are the three support vectors. And now what we can do, uh, these three support vectors now, these are the three support vectors. At first, what we have to do, we can augment those support vectors. The augmentation is by adding another dimension, and that dimension is just putting the 1 here. Here is 1, here is 1, and here is 1. So this is called the augmentation. So support vector augmentation. So that means here the S is augmented to S tilde by adding extra dimension, and then the value is 1. Here is this 1, and here is this 1. This is called the augmentation. So we can augment the data set like this way. And now after augmentation, we need to form the equations. Okay, form the equations for each and every support vectors. So in this case, we can see we have three equations. Actually, these equations are our Lagrangian equations. Okay, so we already discussed that is in details how to form those equations and how to that is form those things. It's the same thing. Directly we can see alpha 1 S1 and S2, then alpha 2 S1. So in our first equations, the support vector, we can see that the support vector 1 will be the constant. So we can see here, this is support vector 1. Here is also support vector 1. Here is also support vector 1. Okay, that is augmented support vector. And the another one, that is here the S1, S2 and S3 is changed. Okay, those are the changed. And S1 we have taken, the support vector we have taken from negative class. So that's our negative. If we can remember the equation what we have discussed here. So we can see that actually here is our KAA. Okay, KAA. What is it? Is the support vector A and support vector A. We have multiplied these two. We have multiplied these two, and then here's the alpha A. The same thing here. Actually, the same equation, same thing we are doing here. You can see here KAA, that is here A is the support vector, A is another support vector. This is also the same. Okay, so we are determining the KAA, and then it is what? It is the KBA, and then this one is the KCA. And alpha A, there is here it is mentioned alpha 1, here is alpha 2 and alpha 3. Okay, alpha 1, alpha 2 and alpha 3. Okay, now we can see that it is equal negative 1, that means negative plus, and then we have already taken that one also in our equations, in that equations. Here we can see this is equal negative 1, because this A, it is taken from the negative class. Okay. Similarly, we can form another equation. This is another equation. That is, this time we have to fix the S2, that is support vector 2, support vector 2, support vector 2, and we have to change the others, like S1 here is S2 and S3, alpha 1, alpha 2, alpha 3. Here S2, we are fixing S2, that is support vector 2, and also the support vector T is from the negative class, so here is the negative. Similarly, we can see here that is alpha 1, S1, and then S3. That means we have to fix the S3. There is the S3, there is the S3, and then S1, S2, and S3. The S3 we have taken from the positive class. That's why here is the positive. Okay. So now these are the three equations. Then what we have to do now? Put the values of S1 tilde, S2 tilde. So that means that is augmented support vectors. The values of augmented support vectors. And now we can see alpha 1, this 2, this 2. Okay. Uh, we have to form the equation now. That means these are the two vectors we need to multiply. So for that, what we have to do, like 2 times 2, 2 times 2, this 2 plus of 1 times 1, 1 times 1, and then plus of 1 times 1. So it is 4, 1, 5, and 1, 6. That is 6. So we will get here 6 alpha 1. Okay, 6 alpha 1. And that's how we have decided that is determined also KAA. Okay, KAB, KAC. Okay, in our previous example, the same thing here. Okay, so if we have multiply those the augmented support vectors, corresponding augmented support vectors, then we will get these three type of equations. Okay, these three equations, and we can see that we have three unknowns: alpha 1, alpha 2, alpha 3. We have three equations, so we can easily, by solving these three equations, we can easily find out the alpha 1, alpha 2, and alpha 3 values. And you will get, in this case, alpha 1 equal alpha 2, it is minus 3.25, and alpha 3 equal to 3.5. So we will get you will get this. And now so we solve that and also find out the alpha 1, alpha 2, and alpha 3 equation. And now what we have to do, we have to use this equation to find out the W value. Okay, so W equals summation of alpha I and Si. So summation of alpha I and Si. So in this case, you can see that is we know the alpha I and we know the Si also. So alpha, we have decided the values of that, and the augmented support vectors also we know those. So now if we just follow this equation, then we will get this. This is what? This is our W and B. That means augmented W. So in our augmented W, we have the W and B. So in this case, it is also two-dimensional data. So we will get the first two. This is the objective. So this will be our W, and B is our -3. So this is the B. So that means W is 1, 0. The vector W is 1, 0. So we can see here the vector W is 1, 0, and B is -3. Now we need to find out our equation of the support vector. So here is the W transpose X plus B equals 0. And the W is 1, 0. We can see here 1, 0. If we transpose it, then we will get there is 1 and 0. And as we can see, we have two-dimensional data. Again, we will get the hyperplane as the line. So here X and Y and B. Okay, so if we put the value of B is -3, so B is -3, is -3, and we can say 1 times X, that is X, 0 times Y, so Y will be 0. So X minus 3 equals 0. X minus 3 equals 0. It means X equals 3. So this will be our hyperplane equation. This will be our hyperplane equation, and we know that there is X equals 3. So it is a parallel to our y-axis. Okay, parallel to our y-axis. So this is the equation. This is our hyperplane. In this case, we can see at the point 3, this is a parallel line to our y-axis. So y is what? Here is x2. And now So that means equation, we got the equation, we plot our hyperplane, and then the next thing is we can test maybe whether our model can correctly classify the positives to positives and negatives to negatives or not. So we know that we assume that this side is negative and this side is positive. Okay, this side is positive. Now maybe a new point like 1, 2. So our hyperplane equation, we know that the hyperplane equation is x3. Okay, so now we just plot here. The w is 1, 0, and the data point is here. The x is 1 and 2, so 1 and 2, and b is -3. We know this, we have already computed the optimal value of b. And then if we just plot it here, then we will get here -2. -2 means the negative is the negative class. So it means that this point is in negative class. And if we can see in our that is plot, we can see 1, 2. The point is 1, 2. So 1, 2. You can see here 1 and 2. 2 is 1. 2, 2 is this. So the point will be in this case. And we can see that this side is negative side. Okay, negative side. So that means this is negative. This is negative, and it is correctly identified as negative. So let's test another one, that is 6 minus 1. Uh, just put those values here, and we will get here that is the 3. So uh, 3 means it is in positive side. So it is in positive side. And now if we just 6 minus 1, if we want to plot here 6 minus 1, and we can see that here is the 6 and minus 1, the point will be in this position, and we can see it is in positive side also. So that means it is correctly classified the positives. Now the next thing is our nonlinear problem. So if we have nonlinear problem, that means you can say it is not linearly separable. So like if the data points we have, the data points are here, one data point, this is another, this is another, and this is another. The data this way, then we can see that actually it is not possible to draw just a single line here, like maybe this one, to classify positives from the negatives. So then what can we do? So we can do like maybe if we can draw the curve, then we can select the positives from the negatives, considering the blue circles as the negative and the red squares as the positives. Okay. So that means we can see that actually it is not possible to draw a linear line. Like we cannot draw the line to separate all positives and negatives. So that's our nonlinear SVM problem. Nonlinear SVM problem. So to deal with the nonlinear SVM problem, usually the support vector, it considers some form of kernel trick, or we can say kernel function. So it will uh, transfer the points in a new feature space, in a new feature space, in a new feature space, and after that it will apply the our linear support vector algorithms. Okay, support vector classification algorithm. So consider that these are the data points, and for in this case we have the blue class vectors, that is we can say negative vectors, and red class vectors, that is called the positive vectors. So these are the vectors, these are the points. So we can see this one is what, this one is 1 1. So here is the 1 1. Okay. Similarly, this one is 2 0. Okay, so here is the 2 0. Okay, this is how we can plot all those vectors. Now we need to find out a kernel trick or kernel function. Kernel trick is also a
Sir,
function, but hello, bolo.
hello, sir. I have another class now.
Other class.
Yes, sir.
What can we do? Uh, okay, I think we should stop here then. If you have another class, so our class is up to 12:30 maybe.
No, sir, it's still 12:20.
Oh, 12:20. Okay. Okay, then we will start our discussion from this slide in our next class.
Thank you, sir.
Okay, thanks all of you for joining in this session.
Thank you, sir.
Assalamualaikum, sir.
Alaikum salam.